Lately, we have been exploring numerical integration. These techniques help us to approximate the definite integral of a function. Graphically, that amounts to estimating the area beneath a curve over a specified range. We've looked at the Trapezoid Rule quite a bit. If you missed those lessons, I strongly suggest you review them before we proceed, because today we are going to introduce Simpsons Rule by following a similar derivation from the Taylor series. Look at the graphs shown here. I have divided a region into three panels, P1, P3, and P5. If I subtract P1 and P3, that leaves me with only P5. That is the foundational idea we are going to use to build the rest of this method. Notice that area from x0 to x6 is represented by I of x6. I for integral, if that helps you conceptualize it. Likewise, area from x0 to x4 is represented by I of x4. P5 equals I of x6 minus I of x4. That's simply what we saw on the previous slide. That can be generalized to any P sub j, as seen equivalently in the last two lines. The second line is in index notation, whereas the h's in the third line set me up for a Taylor series expansion. These are the Taylor series expansions for I of x plus h and I of x minus h. Notice the alternating positive and negative signs in the second row. If I subtract one from the other, notice which terms cancel out and which ones double. The final result is displayed in the third line. As we did when deriving the trapezoid rule, we now replace i's with f's. F double prime can be replaced by a central difference representation. We covered these in a previous lesson as well, so feel free to check that out if you have any questions on where this came from. Here is the substitution of that. The third line is the final result once we've distributed, collected like terms, and cleaned up a bit. The result of the previous slide is repeated in the first line here for convenient reference. Next, I can represent P1, P3, and P5 by plugging those values into the subscript every time I see a J. Notice the terms in red and blue. They will combine when we add the three panels together. That is shown here. Total area is the sum of the three individual panels seen on the second slide of this lesson. If we were to increase the number of panels, the pattern would be more apparent. Notice the first and last term, f0 and f6, are multiplied by 1. Every odd term between them is multiplied by 4, and every even term is multiplied by 2. We will revisit this pattern when we implement Simpsons Rule to calculate a definite integral. Now we must talk about the error terms. In purple, I am employing the mean value theorem to represent the fourth derivative of a single x value, rather than the sum of the fourth derivative at every point. This was explained more thoroughly in our lesson on the trapezoid rule. There are slight differences, but the same idea applies. One specific difference is that we divide by 2h. This is because one panel for Simpsons Rule is twice the width of a trapezoidal panel. In green, we see that this term is reduced from 7th order to 6th order. The final result is shown on the last line. If you remember, we applied end correction to the trapezoid rule to improve its accuracy. This was done by tweaking the purple term. Unfortunately, that process is not as straightforward for Simpsons Rule, so we won't pursue that option here. Notice, however, the h to the fourth over 180. This is still fourth order, which is pretty good. The final result is summarized here using sigma notation for summation. Thus it is that the Taylor series have given us yet another useful method to make meaningful numerical approximations. We will use Simpsons Rule to compute a definite integral in the next lesson, and then compare our answer to previous results. Stick around for that.